Hi there, and welcome to the Science Sleep, where gentle science meets peaceful rest. Tonight, we invite you to drift with us far beyond the rhythms of the human mind, into a realm where creation begins in silence, the birth of stars, how stellar nurseries create suns. Together, wander through the dark, dust-filled cradles of the cosmos, where gravity whispers, clouds gather in slow motion, and the first sparks of future suns begin to glow. Follow the quiet collapse of ancient gas, the delicate dance of light and shadow inside nebulae, and the moment when a newborn star takes its first luminous breath. So breathe slowly. Let your thoughts expand like the night sky, and allow science sleep to guide you into the calm, cosmic science of how the universe creates its brightest lights gently, patiently, and always in the dark. In the deep quiet of the universe, far beyond the glowing arms of spiral galaxies and the orbits of familiar planets, there exist vast regions that appear almost empty to the human eye. These regions are cold, dark, and silent, yet they cradle the most delicate and extraordinary processes of cosmic creation. Astronomers call them molecular clouds, but poets might call them wombs of the universe. They are immense drifts of gas and dust, stretching for dozens or even hundreds of light years, forming soft, shadowy structures that hang like veils between the stars. From a distance, these clouds appear serene, as though frozen by the great stillness of space. But inside them, hidden behind curtains of dust, something vibrant and restless is always unfolding. These are stellar nurseries, the birthplaces of suns. Every star you have ever seen, every warm sunset on Earth, every distant point of light that gleams from the sky began its story in a place like this. The primary ingredient of these clouds is hydrogen, the simplest and most abundant element in the universe. Alongside, it drifts helium, as well as trace amounts of carbon, oxygen, nitrogen, and tiny grains of silicate dust, the ashes of ancient stars that died long before our own solar system formed. Space is not filled with chaos. It is filled with memory. And every star born today is shaped from the remains of stars that burned billions of years ago. Molecular clouds are incredibly cold, often only a few degrees above absolute zero. In this frigid darkness, hydrogen molecules move slowly, conserving energy, drifting lazily through the void. But despite their low density, far emptier than the best vacuum humans can create, these clouds contain enormous amounts of mass. A single cloud can hold enough material to form thousands of stars, as large as our sun. Yet this material spreads thinly across space, waiting for something to disturb its fragile balance. Gravity is always present, always pulling, always patient. It does not rush. It does not force. It simply waits for the smallest imbalance. Inside the cloud, turbulence swirls from ancient shockwaves. Winds from nearby massive stars carve shapes into the gas. The faint pressure of starlight pushes ever so gently on dust grains. And over millions of years, these subtle motions create pockets where gas becomes slightly denser than the surroundings. A region just a little heavier than the rest begins to contract. More gas drifts toward it. The region grows denser still. Gravity strengthens its hold. The collapse becomes inevitable. Slow at first, then faster as mass gathers. Inside this growing knot of gas, pressure rises, temperature climbs, molecules collide more frequently, and the first hint of something new begins to emerge. Astronomers call these regions dense cores, small, compact cocoons inside the greater cloud. Compared to the vast nebula that surrounds them, they are tiny, but they contain everything needed to form a new star. The cloud around them dims their light, hides their heat, and protects their fragile beginnings. In the earliest stages, nothing about them appears bright or dramatic. But deep within, hydrogen atoms are being pushed closer together, and the laws of physics, unchanged for billions of years, are beginning to steer this material toward an extraordinary transformation. As the core collapses, it rotates. Even a tiny initial spin becomes faster and faster as the cloud contracts like an ice skater pulling in her arms. This rotation prevents all the gas from falling directly into the center. Instead, it forms a swirling disk around the growing core, a structure that flattens into a thin, rotating plane of dust and gas. This disk will one day become the birthplace of planets. But for now, its main purpose is to feed material into the forming star. Meanwhile, the core at the center grows hotter. Gravity squeezes it relentlessly. Temperatures rise into the thousands of degrees. The material becomes ionized, turning into plasma matter, so energetic that electrons break away from their nuclei. The protostar is emerging, a sphere of hot gas that glows faintly with the heat of its formation. But it is still hidden within thick blankets of dust. From the outside, there is no sign of a new star, only darkness. Inside, pressure builds toward a critical threshold. Hydrogen atoms are packed tightly, colliding with increasing intensity. Their motions reflect a fierce internal struggle. Gravity pulls them inward. Heat pushes outward. The protostar is trapped between collapse and resistance. It is not yet stable. It is not yet shining. It is a star in waiting. Powerful jets erupt from its poles, narrow streams of charged particles blasting outward at hundreds of kilometers per second. These jets carve tunnels through the surrounding cloud, creating glowing cavities that astronomers can detect even when the star remains invisible. They act as release valves, allowing the protostar to shed angular momentum, stabilizing its rotation so it can continue to grow. Without these jets, the forming star might tear itself apart. The disk surrounding the protostar swirls faster, feeding gas inward. Material spirals into the core like water funneling into a drain. Each particle adds mass. More mass means more gravity. More gravity means more heat. The core climbs past 10,000 degrees, then 100,000. At these temperatures, matter behaves in ways that defy ordinary experience. Electrons move at tremendous speeds. Nuclei vibrate violently. Pressure rises to unimaginable levels. At the center of the protostar, where the density is highest, hydrogen atoms are being forced so close together that their protons nearly touch. They repel each other strongly, positive charges resisting positive charges. But gravity insists, pushing inward with overwhelming force. Heat insists, accelerating the particles into increasingly energetic collisions. And eventually, a collision will be so intense that two protons overcome their mutual repulsion, binding through the strong nuclear force. This is nuclear fusion, the engine of stars. It releases energy not as chemical heat, but as pure mass converted into light by the equation E equals mc squared. This transformation, astonishing in its power, will fuel the star for millions, billions, or even trillions of years, depending on its size. But in this moment, the protostar does not yet sustain fusion. It is still gathering strength. For now, its light remains trapped. Dust grains absorb the heat, preventing it from escaping into space. From afar, the cloud appears almost unchanged. A dark day ATS, cool region with faint hints of glow. But inside, the drama of stellar birth is accelerating. The protostar contracts more. Temperatures soar. Pressure intensifies. Every moment brings it closer to ignition. The universe is patient, but it is also precise. When the core reaches about 10 million degrees Celsius, fusion will ignite in earnest. Hydrogen nuclei will fuse steadily into helium. Radiation from the core will push outward, balancing gravity for the first time. And at that moment, darkness will give way to light. A star will be born. But before that happens, the cocoon holds tight. The forming star remains wrapped in shadows, hidden from the galaxy that will one day see it shine. It is gathering itself, preparing for the moment when the balance of forces changes forever. Inside this protected chamber, everything is in motion. Particles colliding, matter spiraling, gravity sculpting the future. The birth of a star is not an explosion. It is a slow becoming. A long, quiet negotiation between collapse and heat, between darkness and the promise of light. It is a reminder that creation often begins invisibly, silently, and far from the gaze of any observer. In this vast, cold cradle of gas and dust, a seed of light is forming. A future sun, a future source of warmth, gravity, energy, and maybe even life. It waits. It gathers. It grows. And soon, but not yet, it will ignite. The protostar continues its long inward collapse, held in a delicate tension between the force that pulls everything together and the heat that fights against that pull. It is a quiet struggle, invisible from the outside. But inside the dense core, the movements of atoms are becoming frantic. Hydrogen particles ram into each other with growing intensity, trying to find stability in a space where stability is impossible. The growing heat stirs the interior into a kind of boiling chaos. Every motion is faster than the last. Every collision louder in the language of physics. In these conditions, the protostar is no longer just a collapsing ball of gas. It is becoming a laboratory of extreme conditions, a place where the ordinary rules of matter begin to bend under the pressure. Electrons detach from nuclei, creating a charged soup of particles. Magnetic fields twist and stretch across the interior, shaped by the star's rotation and the movement of its plasma. The protostar's heartbeat grows stronger, though no true pulse has formed yet. It is still waiting for the moment when nuclear fusion becomes stable enough to hold gravity at bay. Around this growing sphere of heat, the disk continues to swirl. It is flattened through rotation, shaped into a thin, vast halo of dust and gas orbiting the forming star. Every grain within it follows the relentless curve of gravity, tracing wide arcs that slowly tighten over thousands of years. This disk is not a passive feature. It is an engine of creation. Gas falls inward. Dust clumps together. Some grains collide and stick. Others bounce, ricochet, or fragment. But over time, collisions build larger structures, pebbles, then boulders, then planet-sized embryos. The seeds of worlds form in the shadow of the star that is itself still unborn. Deep inside the protostar's core, the temperature crosses 1 million degrees Celsius. This is still far too cool for sustained nuclear fusion, but it marks a critical point. The protostar is now radiating heat, not from fusion, but from the gravitational energy of its own collapse. Every second, the star shrinks a little more. Every second, it becomes denser. This contraction releases energy that makes the forming star glow with a faint, hidden light. Outside, the nebula remains dark. Dust absorbs much of the radiation, trapping the heat inside the protostar's cocoon. If an observer were nearby in a spacecraft, they would see only billows of shadow and glowing infrared arcs, the faint signatures of a star still cloaked in its birthplace. But the observer would also feel the immense energy brewing behind the curtain. The region vibrates with potential. The nursery is alive with the subtle tension of something extraordinary preparing to happen. Gravity is patient, but it is also relentless. It does not ease up. It does not pause. Every atom in the protostar is pulled toward the center, accelerating as the radius shrinks. The density rises to levels almost unimaginable from a human perspective. A teaspoon of the material in this core would outweigh mountains. The heat surges higher, approaching 10 million degrees, the ignition point for hydrogen fusion. At this temperature, the collisions between hydrogen nuclei become so violent that they begin to fuse reliably. The moment fusion begins, it is not yet a star. Fusion must become steady. It must become self-regulating. It must last long enough for the outward pressure of radiation to balance the inward force of gravity. This balance, hydrostatic equilibrium, is the defining characteristic of a true star. In the final stages before ignition, the protostar behaves wildly. Its surface is turbulent, rippling with shockwaves of heat and magnetic storms. Powerful winds form around it, driven by intense radiation and rapid rotation. These winds blow outward across the surrounding disk, sweeping away loose gas and sculpting the region with arcs of energy. Jets of plasma shoot from the poles, stretching for light years, illuminating the surrounding cloud with faint blue and red hues. Each jet carves a path through the nebula, creating cavities through which the new star will eventually reveal its first light. Meanwhile, dust grains within the disk absorb radiation and reflect it outward, creating a subtle glow. These grains are microscopic, less than 1,000th of a millimeter, yet they hold tremendous importance. They will become the building blocks of planets, comets, moons, and asteroids. Without dust, suns might still form, but worlds like Earth could not. Life, at least as humans understand it, would be impossible. Back in the core, fusion intensifies. hydrogen nuclei collide with such force that they fuse into helium, producing neutrinos and gamma rays. The gamma rays struggle to escape the dense plasma. Each photon is absorbed and re-emitted thousands, millions, even billions of times before it finally reaches the surface. Because of this, the energy generated at the center may take hundreds of thousands of years to emerge as visible light. This internal struggle for escape marks the transition from protostar to true star. The temperature stabilizes. Radiation pushes outward. Gravity pulls inward. For the first time, the forces are balanced. The protostar, after millions of years of silent collapse, becomes a star. Nuclear fusion is now stable. The core shines with steady power. The long night inside the nebula begins to lift. But even now, the newborn star remains hidden. Dust still encloses it. Its light must carve its way out, pushing through layers of gas that cling to its surface like fog to a lantern. The stellar winds grow stronger, blowing away the last remnants of the cocoon. The jets weaken. The rotation slows. The star begins to calm as it enters its long main sequence life. Eventually, the dust thins enough for light to escape. A soft glow spreads through the nebula. Shadows dissolve. The surrounding gas begins to sparkle with ionized brilliance. What was once a dark nursery becomes a luminous cloud, glowing with the presence of the star it protected for so long. This moment, the emergence marks the true birth. The star's first visible light reaches the universe, traveling outward in every direction. It is a declaration, a beginning, a new point of illumination added to the tapestry of the cosmos. Planets are already taking shape in the disk around it. Some will become rocky worlds. Others will be gas giants. Some may be shattered in collisions. Some may drift too close and spiral into the star. But the process has begun. The architecture of a future solar system is quietly forming in the afterglow of the newborn sun. The nebula that once sheltered the star will eventually disperse. Winds from other stars, radiation, and the passage of time will dissolve it into the galaxy. But for now, the nursery still holds traces of light blues, reds, and golds shining through cosmic haze. It is a reminder that creation often begins in the dark, and the brightest things in the universe are born from shadows. Every star in the night sky once lived this story. Every sunrise on every world began with a cloud collapsing around a tiny point of gravity. Every warm beam of light that has ever touched a planet's surface was ignited in a moment like this, the moment when gravity forced hydrogen to shine. And every atom of carbon, oxygen, nitrogen, iron, and every element that makes life possible was once forged in a star born from the same quiet process. When humans look up at the sky, they are not seeing distant strangers. They are seeing family. They are seeing the cosmic ancestors that gave rise to all matter, all planets, all oceans, all creatures, and all consciousness. The universe writes its story in stars, and every star begins as a whisper inside a dark cloud. And so, the cradle of creation remains, silent, cold, waiting for the next disturbance, the next collapse, the next gathering of dust, waiting for the next star to breathe its first light into the endless night. Gravity begins not with thunder, but with a whisper, a subtle imbalance, a faint gathering of particles in a quiet corner of a cosmic cloud. It is one of the most patient forces in the universe, and one of the most decisive. It does not shout, nor does it rush. It simply pulls, softly at first, then with increasing certainty, until the structure of an entire nebula begins to shift around it. Inside, a molecular cloud, gravity behaves differently than humans might expect. There is no sudden collapse, no dramatic implosion. Instead, the material within the cloud drifts, brushes, gathers, and compacts over impossibly long periods of time. A tiny region becomes slightly denser than the rest. Just a few more atoms per cubic centimeter. Almost nothing from a human point of view. But in the language of the cosmos, this difference is destiny. Once this denser region forms, gravity grows stronger there. More gas is pulled inward. The region becomes heavier still. The gravitational pull increases. This feedback loop is slow but unstoppable. It is the beginning of a collapse that will one day ignite a star. As the gas collapses inward, it does not fall in a straight line. It swirls. It curls. It rotates. Even the slightest initial rotation becomes more pronounced as the region shrinks. Conservation of angular momentum forces the spin to accelerate the cosmic ballet of forming suns. This growing rotation will later flatten the surrounding material into a disk. But for now, it simply marks the beginning of order within chaos. Deep inside the collapsing core, pressure begins to build. Molecules are squeezed tighter and tighter. The temperature begins to rise, not from fusion, not yet, but from the energy of gravitational compression. This is known as gravitational heating. It is the same principle that warms your hands if you squeeze them together, but magnified on a scale so large that the numbers lose meaning to ordinary intuition. The core contracts. The temperature climbs into the hundreds, then thousands of degrees. The gas becomes opaque. Light, such as it is, cannot escape. The entire region becomes a warm, glowing seed buried inside darkness. Still, no light breaks out, because the cloud around the core remains thick with dust. This dust is ancient, the crushed remains of old stars and forgotten worlds. It absorbs and scatters light, keeping the forming protostar hidden from view. Outside the collapsing core, the molecular cloud responds to the disturbance. Shock waves ripple through the gas like waves through water. Some regions become compressed, others stretched. Small filaments form, creating strand-like structures that connect dense cores across tens of light years. Gravity does not work alone. Magnetic fields thread through the cloud, sometimes slowing collapse, sometimes guiding the motion of ions and particles. Turbulence stirs the gas, generating pockets of pressure that resist gravity's pull. It is a delicate balance, a war fought in slow motion between collapse and chaos. But gravity persists, and slowly, the collapsing core swells in importance. It becomes the gravitational center of its environment. Material flows toward it from all directions. Streams of gas fall inward through channels carved by magnetic fields and turbulence. Some of this gas will eventually reach the center and help ignite the star. Some will join the rotating disk that forms around it. Some will be ejected by jets when the forming star tries to regulate its angular momentum. But for now, everything is being drawn inward, step by patient step. The contraction accelerates. The core grows denser by many orders of magnitude. Hydrogen molecules slam into one another with growing frequency. Collisions generate heat. Heat increases pressure. Pressure slows collapse. But gravity continues to pull. And the core? This battle gravity pulling inward, pressure pushing outward, defines the early life of a forming star. If gravity wins completely, the core collapses violently. If pressure wins too soon, the collapse halts and the star never ignites. Only when the two forces begin to reach a delicate equilibrium does the protostar truly emerge. As the core heats and contracts, something remarkable happens. The gas around it begins to glow in infrared light. Humans cannot see this glow with their eyes, but telescopes reveal it as a warm, soft luminescence within the dusty cloud. Infrared light slips more easily through dust, allowing astronomers to peek at the earliest stages of star formation. They see mottled shapes, bright knots, swirling arcs, the first hints of a star waiting to be born. The collapsing material emits energy not just in the form of heat, but through radiation, magnetic disturbances, and powerful outflows. The rotation of the core helps channel some of this excess energy into jets that blast outward from the poles. These jets are astonishing in their scale. Narrow beams of plasma stretching for light years, moving at hundreds of kilometers per second. They punch holes through the surrounding gas, carving luminous cavities. These cavities reveal the presence of the forming star long before the star itself becomes visible. Meanwhile, the disk around the protostar stabilizes. It thins out. It becomes a flat, rotating platform of cosmic debris. Here, dust grains begin to collide. Some stick, some shatter, some melt together. Static electricity helps tiny grains cling. Gravity binds larger pieces. The earliest seeds of planets, called planetesimals, begin to take shape. Planetesimals, 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 confriend. But their story comes later. The star must form first. Gravity continues to drive the collapse. The temperature in the core rises past 2,000 degrees, hot enough to break molecular hydrogen into atomic hydrogen. This process absorbs energy, briefly slowing the temperature rise. But collapse continues. Heat returns. The core grows hotter. The pressure pushes outward, but not enough to stop gravity's insistence. At around 10,000 degrees, the gas becomes fully ionized plasma. Electrons roam free. Nuclei collide violently. The protostar's interior becomes a glowing, churning ocean of charged particles. Convection currents carry hot material upward and cooler material downward. Magnetic fields twist into loops and arcs, shaping the young star's surface into a roiling, chaotic landscape. Still, no nuclear fusion burns in the core. The heat is not enough yet. The pressure is not enough yet. Gravity has not completed its work. Outside the protostar, winds intensify. These winds, driven by heat, rotation, and magnetic pressure, sweep away excess material. The cloud around the forming star begins to thicken with motion. Streams of gas flow outward from the poles and inward along the equator. ATI, with maybe one ATI. The entire nursery glows faintly in infrared and radio frequencies. It is like watching a distant fire through smoke, warm and flickering, but still hidden. Deep inside, the temperature climbs toward 1 million degrees. This is a milestone. Not yet the ignition point, but a sign that the core is approaching the conditions necessary for hydrogen fusion. The collapse slows slightly as heat increases. But gravity remains stronger. It must compress the star until fusion ignites. Only then will balance be achieved. The cloud outside continues to feed the growing protostar. Material falls inward along spiraling paths, adding mass, releasing energy, and heating the core further. Every new atom that joins the collapsing region brings the star closer to ignition. The protostar brightens, though still hidden by dust. Its surface roils with convection. Jets widen their cavities. The disk spreads outward. The gravitational well deepens. At this stage, the forming star is unstable. It pulsates faintly. It expands and contracts. It absorbs and releases energy in erratic waves. These oscillations create shock fronts that ripple through the surrounding gas. Some shocks compress the nearby material, potentially triggering the formation of additional dense cores, siblings in the same stellar nursery. Gravity does not create just one star at a time. Most stars are born in clusters. Some are born as twins, some as triplets, some as entire families spanning dozens of suns. These clusters may drift apart over millions of years, but their origins are entwined forever. Even our sun is believed to have been born in such a cluster, though its siblings have long since wandered into the arms of the Milky Way. Back in the collapsing core, the temperature approaches several million degrees. Pressure mounts. The very nature of matter begins to shift. Hydrogen nuclei are squeezed into such close quarters that the energy of their collisions approaches the threshold of fusion. The protostar is on the edge of awakening. It is a moment of cosmic tension, the universe holding its breath. The collapse continues. Gravity whispers louder. Heat pulses outward. Jets carve deeper channels. The disk spins like a vast cosmic whirlpool. The protostar glows hotter with each passing millennium. Soon, very soon, in cosmic time, hydrogen nuclei will fuse. The process will become self-sustaining. Pressure will push outward, balancing gravity. The protostar's long fall inward will end. A star will ignite, but not yet. This is the last deep breath before creation. The final tightening of gravity's embrace. The last moment of darkness before a new point of light enters the universe. Inside the collapsing core, time seems to behave differently. Not truly slower, but stretched across the vastness of cosmic events. What takes millions of years unfolds as gently as a sigh in the darkness of the nebula. Gravity has guided the protostar through its earliest, most fragile stages, and now the collapse enters a phase of unstoppable momentum. Material flows inward like a cosmic river, channeling gas toward the center with increasing intensity. Every particle that falls adds heat, adds pressure, adds mass. and brings the protostar closer to the critical threshold it has been approaching since the first atoms gathered. The temperature in the core now surges beyond 3 million degrees Celsius. At these temperatures, atomic nuclei behave like living projectiles, hurling themselves into collisions with tremendous energy. Still, the conditions are not yet extreme enough for steady fusion. But the stage is set. Every shift, every collapse, every rotation points toward the same inevitable outcome. Around the protostar, the disk continues its transformation. This swirling band of dust and gas grows thinner and more structured as time passes. Faint spiral arms form within it, sculpted by gravitational interactions and turbulence. Larger clumps of dust begin to gather in patches of enhanced density. These are the first hints of future planets, though they are still nothing more than drifting clusters of rock and ice no bigger than mountains. The jets that shoot from the star's poles remain powerful. They act as the protostar's way of regulating its spin, preventing it from collapsing too quickly from angular momentum. They also clear away the surrounding cloud, carving paths that will one day allow the star's light to escape. These formations, called Herbig-Haro objects by astronomers, glow as the jets slam into the surrounding gas, heating it to temperatures that make it shine in visible light. They are like the first murmurs of the newborn star, faint but undeniable. Meanwhile, the protostar itself is becoming increasingly luminous. It shines not because fusion burns in its core, but because gravity continues to convert potential energy into heat. This glow radiates outward in infrared wavelengths, slipping through the dust more easily than visible light. If humans could look at this forming star with infrared vision, they would see a warm, bright sphere nestled deep in the heart of the nebula, glimmering like an ember in a pile of ash. But the protostar is restless. Its surface churns with convection currents. Hot plasma rises and cool material sinks. Magnetic loops arc into the surrounding space. Shocks ripple across the outer layers. The star pulses faintly, as though breathing. Inside the core, pressure builds to godlike proportions. Hydrogen atoms, once free and drifting, are now packed together in a dense plasma, colliding billions of times per second. The electrons are stripped away, leaving a chaotic soup of protons and electrons swirling at incredible speeds. The core has become a furnace, hot, compressed, and ready for the next phase of transformation. At around 10 million degrees Celsius, a threshold is crossed. The collisions between hydrogen nuclei become energetic enough to overcome their electrical repulsion. The strong nuclear force, a fundamental interaction that binds the nuclei of atoms, takes hold. 2 protons fuse. A chain reaction begins. The first stable reaction is the proton-proton chain, the dominant fusion process in stars the size of the Sun. When 2 protons fuse, one transforms into a neutron, forming a deuterium nucleus. More collisions follow, forming helium-3, then helium-4. Each step releases energy in the form of gamma rays, positrons, and neutrinos. These particles race outward, colliding, scattering, and slowly converting the core's furious energy into the light that will one day shine across the cosmos. But at first, fusion is sporadic. It flickers. It pulses. It is not yet stable. Gravity continues to push inward, trying to compress the star even further. Fusion pushes outward, trying to expand it. For a brief period, the star oscillates between collapse and explosion. It grows brighter, then dims. It expands, then contracts. But slowly, steadily, a balance emerges. Hydrostatic equilibrium. The great cosmic peace is reached. Gravity is matched by the radiation pressure from fusion. The core stabilizes. The churning subsides. The protostar becomes a true star. This is the moment of ignition. A moment that, though it unfolds over thousands of years, is the closest thing the universe has to a cosmic birth cry. The star now shines. Self-sustaining light. Its core burns with fusion. Its surface radiates heat into the surrounding nebula. Its winds intensify, blowing away the remnants of the cocoon that once sheltered it. The dust surrounding the star begins to glow with new vigor. Ionized gas lights up in spectacular colors, reds from hydrogen, blues from oxygen, greens from sulfur. The nursery that once held the star in darkness now becomes a luminous display, a neon cloud marking the birthplace of a new sun. Meanwhile, the disk continues to evolve. Planetesimals grow larger. They collide more frequently. Some are shattered into fragments. Others merge into protoplanets, bodies tens to hundreds of kilometers wide. These worlds to be are shaped by gravity, by collisions, by turbulence, and by the radiation from the newborn star. The star's gravitational influence now reaches beyond the disk. It organizes the surrounding cloud, sweeping away material in waves. Some of this expelled gas will become part of nearby stars. Some will drift into interstellar space. Some will recombine into new molecular clouds, waiting to begin the cycle anew. Time stretches on. The star grows brighter, hotter, more defined. The cocoon thins. Light escapes through the cavities, carved by jets. The newborn sun steps forward into the openness of the cosmos, shining for the first time, without the veil of its nursery. This moment is breathtaking. The star's first visible light travels outward in every direction, spreading through the cloud, illuminating the structures that protected it. What was once a shadowed landscape becomes vibrant and alive, glowing in hues of violet, red, and gold. Eventually, the surrounding cloud disperses enough that the star can be seen clearly from across the galaxy. It becomes another point of light in the Milky Way, one star among hundreds of billions, yet utterly unique in its formation, its surrounding planets, its future. The newborn star now enters the longest stage of its life, the main sequence. Here, it will remain for millions to billions of years, shining with steady hydrogen fusion. Its winds will calm, its rotation will slow, its magnetic storms will settle. The disk around it will continue forming planets, moons, and asteroids. Life may emerge if conditions allow, but all of that lies ahead. For now, the star is new, clean, bright, balanced. The gravitational whisper that once nudged a few stray atoms together has grown into a luminous beacon of energy. The quiet pull became a collapse. The collapse became a furnace. The furnace became a sunrise. And in thousands of stellar nurseries across the galaxy, the same story is unfolding at this very moment. A tapestry of births scattered across the spiral arms of the Milky Way. Stars are forming in darkness. Nebulae are glowing with their first light. Gravity is weaving the universe together, stitch by patient stitch. When you look up at the night sky, you are seeing not only the stars that exist now, but the echoes of their beginnings. Each point of light is a triumph of gravity over chaos. Each one a testament to the quiet persistence of natural law. Each one a flame ignited in darkness. The cosmos does not rush creation. It allows it. It nurtures it. It waits for the right moment. And when the moment comes, it transforms dust into fire. This is the power of the gravitational whisper. Not forceful, not loud, but steady, ancient, and unwavering, guiding hydrogen atoms into the heart of a star and turning emptiness into illumination. In the heart of the collapsing core, where temperatures climb into the millions of degrees and pressure mounts with every passing millennium, the universe prepares for one of its most delicate transitions. A star is on the edge of awakening. What began as a faint gathering of dust and gas has become a roaring furnace, sealed inside layers of darkness. The protostar has grown massive, hot, and impatient. Gravity has pulled it inward for so long that the collapse now feels almost unstoppable. For millions of years, the protostar has been warmed only by the energy of its own contraction, a transformation of gravitational potential into heat. This has been enough to illuminate the interior of the cloud in infrared, enough to stir the surrounding gas, enough to carve jets across light years of space. But it is not enough to make a star shine. A star is born only when fusion becomes stable, only when hydrogen begins its long journey into helium, only when the outward pressure of radiation finally balances the inward pull of gravity. And now, after ages of quiet preparation, the protostar approaches this final threshold. The core contracts further. Pressure reaches intensities that defy human comprehension. Matter is compressed so tightly that the distance between atomic nuclei shrinks to nearly nothing. Protons, particles that naturally repel each other with fierce electrical resistance, are forced into close quarters. Their collisions become more violent, more frequent, more energetic. The temperature climbs toward 10 million degrees Celsius. This is the ignition point. This is the moment gravity has been shaping since the first atoms drifted together in the molecular cloud. At these temperatures, something extraordinary happens. The thermal motion of hydrogen nuclei becomes so intense that their electrical repulsion, the barrier that has prevented fusion, can be overcome. Protons slam into each other with enough energy for the strong nuclear force to take hold. The first successful fusion reaction occurs. Two protons fuse into a single deuterium nucleus. A neutrino is released, racing away at nearly the speed of light. A positron emerges, annihilating with an electron and creating gamma-ray photons. This moment, invisible and silent, is the spark of starlight. At first, these reactions are rare. A scattering of fusion events flickers across the core. They are not yet steady enough to halt the collapse. But fusion is infectious. Each reaction releases energy. Each burst of energy increases temperature. Higher temperature means more collisions. More collisions lead to more fusion. A chain reaction grows inside the core like a rising tide. The protostar trembles. It expands slightly as energy surges outward. Then gravity pulls it back, compressing it again. It oscillates, struggling to find equilibrium. These pulsations ripple through the surrounding disk, sending waves of motion through the nascent planetary system. Dust clouds shudder, gas streams warp, shockwaves travel outward like ripples on a cosmic pond. The star grows brighter, not in visible light, but in deep, penetrating radiation. Gamma rays from the core are absorbed, scattered, re-emitted, and absorbed again as they try to escape through the dense plasma. It will take thousands of years for this energy to rise to the surface. But the process has begun. The ignition is underway. Meanwhile, in the outer layers, the protostar begins to stabilize. Magnetic storms arc across its surface. Convection currents churn violently, creating luminous patches of hotter and cooler material. The star appears swollen, larger than it will eventually be, inflated by the heat trapped inside. It is a turbulent, chaotic object, a newborn still finding its balance. But the core is becoming organized. A central zone of steady fusion spreads outward as temperature and pressure equalize. Hydrogen begins to fuse into helium in vast numbers. Energy production skyrockets. The internal pressure grows strong enough to push back against gravity. For the first time, the inward collapse slows, not because energy has been exhausted, but because energy is finally being created. Hydrostatic equilibrium approaches. The long struggle between gravity and heat begins to resolve. Gravity pulls inward. Radiation pushes outward. When those forces match, the star will enter the main sequence, the long-burning phase that defines a star's lifetime. But before equilibrium fully sets in, the star undergoes one more dramatic transformation. The jets that once shot from its poles begin to flicker. Their power wanes. Their shape shifts. As fusion stabilizes, the star no longer needs to rely on jets to shed angular momentum. Instead, stellar winds take over, streams of charged particles blowing outward in all directions. These winds push away the remnants of the protostar's cocoon, clearing space for the newborn sun to shine. The surrounding nebula glows in response. Gas is ionized by the stars. Radiation. God is a cheese. God is a cheese. Lighting up in brilliant clouds of color. Hydrogen shines red. Oxygen glows blue. Sulfur casts a faint green. The stellar nursery that once hid the forming star now becomes a stage for its debut, illuminated, shimmering, transformed by the arrival of light. Within the disk, the increased radiation has a profound effect. Some areas heat up, evaporating volatile compounds. Other areas cool, allowing dust to stick more firmly. Chemical reactions accelerate. The architecture of planets becomes more defined. Rings of debris form. Gaps open where protoplanets have eaten or scattered material. The disk hums with motion, shaped by the gravity of the newborn star. Back in the core, the fusion reactions stabilize into a continuous process. Each second, hundreds of millions of tons of hydrogen fuse into helium. A fraction of the mass is converted into energy, the light and heat that will radiate across the cosmos. This is the moment the star becomes self-sustaining. It no longer needs collapse to heat it. It no longer depends on gravitational energy. It generates its own power in a furnace of nuclear fire. At its center, turn 10 ATPC. Turn 10 to this. The star has ignited. It has taken its place in the cosmos as a luminous, all low and compieces, autonomous entity. It will shine now for billions of years, depending on its size, longer, shorter if it is massive. Massive stars burn brilliantly, but briefly, exhausting their fuel rapidly. Small stars burn slowly, lasting trillions of years. Our sun sits somewhere in the middle, a star destined to shine for about 10 billion years in total. But in these early moments, all stars behave much the same. They pulse. They flare. They burn hotter than they will later. They glow with the fierce brilliance of youth. The nebula around the star begins to dissipate. Winds push dust outward. Radiation pressure clears paths through the cloud. Nearby stars contribute their own winds, sweeping material aside. Over time, the cloud thins, revealing the new star in all its brilliance. Eventually, the nursery will fade. Only the star, and perhaps its planets, will remain. The star is now a full participant in the cosmic story. It has joined the billions of suns that populate the galaxy. Its light will travel vast distances. Its gravity will sculpt the space around it. Its heat will nurture whatever worlds emerge in its orbit. It may one day give rise to life, or it may remain a barren beacon in the void. But it has done the impossible. From darkness and dust, it has created fire. From collapse and cold, it has created light. And now it shines, young, bright, burning against the backdrop of the nebula that once held it. The ignition of a star is not a single moment, but a long crescendo of physics, pressure, gravity, and time. It is a symphony played out over millions of years, with a final note that rings across the universe. This is the heartbeat of cosmic creation, the moment hydrogen becomes starlight. The young star, still wrapped in the last wisps of its fading cocoon, continues to settle into the new balance it has earned. Its core burns with steady fusion now, each second transforming vast oceans of hydrogen into helium, releasing energy that pulses outward in every direction. The once chaotic turbulence begins to soften, reshaping into organized layers of plasma flowing beneath the star's surface. It is no longer a collapsing sphere of gas. It is no longer a protostar. It is now a self-sustaining engine of light. Fusion has changed everything. The pressure from the core pushes outward with consistent force. Gravity pulls inward with unwavering strength. These two forces balance so perfectly that the star achieves a new kind of stillness, not quiet, not motionless, but stable. A dynamic equilibrium, a cosmic truce. This equilibrium marks the beginning of the main sequence phase, the stage during which the star will spend the vast majority of its life. For a star like the Sun, this phase lasts about 10 billion years. For smaller stars, it may last trillions. For larger stars, only millions. But no matter the size, the ignition of fusion marks the moment a star finds its purpose. The surrounding nebula, illuminated by the newborn star's light, begins to shimmer with new intensity. The bright radiation tears electrons off atoms, creating glowing patches of ionized gas. These regions form radiant structures, pillars, waves, filaments sculpted by light itself. They are the nebula's response to the star's awakening, the visual echoes of ignition. Radiation pressure expands these glowing cavities, pushing the surrounding dust outward. The star's winds travel outward at high speeds, sweeping away material and creating spherical bubbles of cleared space. The nursery is slowly being carved apart, reshaped by the power of the star it once concealed. A process that began in darkness is now rewriting its surroundings in light. As pressure clears the dust, the star's visible light finally escapes. A warm glow spreads across the nebula, illuminating its sculpted ridges and valleys. The once hidden sun steps out from behind its veil. A brilliant point of light is added to the galaxy. The star has opened its eyes. Meanwhile, the disk of gas and dust that encircles the new star is undergoing its own transformation. Now that the star shines steadily, the disk is warmed unevenly, hotter near the star, cooler farther out. This temperature gradient causes materials to separate by their melting points. Near the star, only metals and rocky minerals can survive. Farther away, ices can remain solid. This distinction lays the foundation for the types of planets that will form. In the inner disk, dust grains collide and fuse into rocky clumps. These clumps grow into boulders, then mountains, then protoplanets. They carve gaps in the disk as they orbit, clearing space and gathering material. They collide fiercely, shattering and rebuilding as gravity sculpts them into new worlds. The architecture of terrestrial planets begins here. Farther out, icy bodies form, growing large enough to attract thick envelopes of gas. These become gas giants, the massive worlds that dominate the outer reaches of planetary systems. Some of these giants will migrate inward. Some will stay where they formed. Some will disrupt smaller worlds with their gravitational pull. The newly shining star orchestrates this entire dance, its radiation and gravity guiding every particle in the disk. But the star itself continues to change. In its first million years of fusion, it is unstable, energetic, and prone to flaring. Magnetic storms erupt across its surface. Loops of plasma arc thousands of kilometers into space. Sunspots, dark regions of intense magnetic activity, come and go like passing weather systems. The star's youth is fiery and restless. These storms send waves of charged particles across the disk, altering chemistry, stripping atmospheres, and shaping magnetic fields of emerging worlds. It is a chaotic environment, but chaos is fertile. It is the necessary turbulence of creation. The young star's rotation is fast, often much faster than it will be later in life. Stars are born, spinning rapidly, because the collapsing cloud transfers its angular momentum into the forming core. This spin stretches magnetic fields across the star's surface and through the surrounding disk. These fields act like cosmic tethers, slowing the star's rotation over time as they transfer angular momentum into the disk and outflowing winds. The star gradually calms. Its flares become less violent, its storms less frequent. Inside the core, the star remains extraordinarily hot and dense. Fusion proceeds at a steady rate, creating a flood of energy that takes thousands of years to reach the surface. When the energy finally arrives, it is released as photons, particles of light, which stream into space at the speed of light. This light travels across the cosmic nursery, bouncing off dust grains, illuminating entire regions of space. Eventually, much of the surrounding nebula will dissipate completely. Some of its material will form additional stars. Some will form planets and comets. Some will drift between the stars, seeding the galaxy with the building blocks of future suns. The newborn star will emerge from its nursery like a young adult stepping out of childhood, ready for the long journey ahead. Yet, even in this moment of emergence, the star's story is deeply connected to what came before. Its existence is the culmination of processes that stretch back billions of years. The hydrogen now fusing in its core was formed in the Big Bang. The dust grains in the disk were forged in the hearts of ancient stars. The carbon, oxygen, and heavier elements came from supernovae that exploded long before this nursery ever existed. The star is new, but its material is ancient. Every atom carries the history of the universe. Now, bound together by gravity and ignited by fusion, these atoms will shine for billions of years. They will give warmth to planets. They will support atmospheres. They will fuel the chemistry of life itself. If life ever arises in this system, it will owe everything to this moment of ignition, the moment hydrogen became light, the formed 9 days in the next wave. The newborn star now joins the galactic ecosystem of energy and matter. Its light will travel across interstellar space, touching regions far beyond its origin. Its gravity will sculpt the future architecture of its planetary system. Its winds will carve the paths of comets. Its radiation will shape atmospheres. Its flares will influence climates. It has become a creator as well as a product of creation. Stars do not live in isolation. Clusters of stars born in the same region will drift apart over millions of years. Some will remain bound by gravity as members of open clusters. Others will scatter across the Milky Way, carrying the memory of their shared birthplace in their chemical fingerprints. Even our sun likely began life in such a cluster, surrounded by dozens or hundreds of siblings that now wander the galaxy far away. But for now, this star remains in the embrace of its nursery. Remention, the glowing gas, the swirling dust, the forming worlds, all are connected by the ignition that has just taken place. But the darkness from which the star emerged now glows with the evidence of its birth. And as the last remnants of the protostellar cocoon drift away, a new sun shines clean and clear against the velvet backdrop of space. Its light spreads outward, shining across the nebula that once hid it, touching every grain of dust, every forming world, every corner of the stellar nursery. The ignition is complete. A new star burns. A new chapter of the cosmos begins. And the ancient cycle continues. Light becomes life. Life becomes memory. This is the power of ignition. It is the birth cry of the universe, the transformation of hydrogen into hope. The moment a star begins its long conversation with the cosmos, the star has ignited. Fusion burns steadily in its core, turning hydrogen into helium. and releasing the light that will shape its destiny. But even with ignition complete, the young star is far from calm. It enters a new stage of life, a turbulent adolescence defined by intense winds, magnetic storms, swirling disks of material, and the chaotic beginnings of future planets. Astronomers call stars in this stage T-Tauri stars, named after a young, flickering star in the constellation Taurus. These stars are newborns, still adjusting to the violence of fusion and the weight of their own gravity. The newborn star is large, much larger in radius than it will be later in life. Heat from its core pushes outward, inflating its outer layers. Its surface boils with convection, carrying energy from deep within upward in dramatic currents. Hot plasma rises, cools, sinks, and rises again, creating a roiling, ever-changing surface. Sunspots' vast regions of magnetic instability appear and disappear in cycles far more intense than those of mature stars. Enormous prominences of plasma arch from the star's surface, looping into space before falling back under gravity. The young star's magnetic field is extraordinarily strong. It twists into knots, stretches into arcs, and reconnects with explosive force, generating flares far more powerful than anything our mature sun produces. These flares send blasts of radiation into the surrounding disk, heating gases and altering the chemistry of the forming worlds. The star's rotation is rapid, often completing a full spin in just a few hours or days. This rapid rotation further amplifies magnetic activity, creating a feedback loop of storms and flares. Yet, despite this turbulence, the star is not alone. It is surrounded by a massive, rotating disk of gas and dust, the protoplanetary disk. We could minute it, reported, with cons. This disk is the remnant of the molecular cloud from which the star was born. It carries within it the potential for planets, moons, comets, asteroids, and perhaps even life. The disk encircles the young star like a cosmic halo, thin at the edges and thick near the center, glowing faintly with reflected starlight. Material in the disk does not move randomly. It orbits the star in patterns shaped by gravity. Faster near the star, slower farther out. This difference in orbital speed creates shear forces that cause dust grains to collide. Some collisions are gentle, forming sticky aggregates of rock and ice. Others are violent, shattering the grains into fragments. But the overall motion favors growth. Step by step, from micron-sized dust to pebble, from pebble to boulder, larger bodies form. At the same time, the disk contains streams and spiral arms, shaped by density waves, magnetic fields, and the gravitational influence of the star. Some regions begin to collapse into clumps, the seeds of future protoplanets. These clumps travel through the disk like young predators, gathering material as they orbit. The more mass they collect, the more efficiently they can sweep up nearby debris. Gravity rewards size. Growth accelerates. Inside the star, fusion stabilizes the core. The internal pressure becomes smooth and predictable. While the star occasionally pulses due to magnetic and convective activity, its overall structure becomes more defined. Hydrogen burns in the core at a steady rate. The outer layers remain inflated, but they are shrinking slowly as the star transitions from protostar to stable main sequence star. This contraction releases additional heat, adding to the turbulence of the star's surface. The young star also emits powerful stellar winds, streams of charged particles, blasting into space at hundreds of kilometers per second. These winds interact with the disk, pushing dust outward, clearing gaps, and influencing where planets can form. Close to the star, the winds are strong enough to blow away lighter materials and ices, leaving only the heavy, rocky ingredients behind. This is why the inner planets of systems like ours tend to be rocky, while the outer planets can retain thick atmospheres and icy shells. The winds also carry angular momentum away from the star, gradually slowing its rotation. This process is essential. If the star kept spinning as fast as it did during collapse, it might tear itself apart. Instead, the magnetic field acts like a cosmic brake, channeling angular momentum into the disk and the escaping winds. Over millions of years, the star's rotation slows to the calmer pace of a mature main sequence star. Within the disk, the interplay between gas, dust, radiation, and gravity becomes a complex dance. Regions of the disk heat and cool unevenly. Some materials vaporize near the star, condense farther out, or freeze into icy grains at great distances. This temperature gradient divides the disk into zones, each with its own chemistry. Near the star, only metals and silicates survive. Farther out, ices can remain stable. Still farther, even volatile compounds persist. This has profound implications for planet formation. Rocky worlds form in the inner disk. Gas giants form beyond the snowline, where ices can accumulate into large cores capable of capturing thick atmospheres. Comets and icy bodies populate the outermost regions, carrying water and organic molecules that may one day seed young worlds with the ingredients for life. Through all of this, the star remains the conductor of the cosmic symphony. Its gravity organizes the orbits of the disk. Its radiation shapes chemistry. Its winds sculpt the disk's architecture. Its magnetic storms inject energy into surrounding gas. Its presence defines every detail of the system's evolution. But the young star is not simply shaping planets. It is also learning to be a star. Its interior structure continues to evolve. Convection dominates much of the interior, transporting energy efficiently. Over time, convection will retreat to the outer layers as radiative zones form deeper within the star. This internal shift stabilizes the star, reducing the magnitude of magnetic activity. Sunspots become fewer. Flares become less frequent. The star begins to settle into a more predictable rhythm. As the star stabilizes, the disk becomes more structured. Ring-shaped gaps appear, carved either by newly forming protoplanets or by pressure gradients. Dust in these rings glows in the starlight, creating luminous bands across the disk. Where protoplanets grow large enough, they generate spiral patterns, their gravity tugging subtly on the surrounding material. These spirals are visible to telescopes as swirling arms of dust, each one marking the birth of a new world. The disk also thins over time. Material falls into the star, drifts outward, or is ejected by turbulence. Jets weaken as the star sheds the last remnants of its angular momentum. What was once a dense, dusty cocoon becomes a wide, open structure of gas and debris. Eventually, the inner regions may clear completely, leaving a thin disk of material farther out, the precursor to an asteroid belt or Kuiper belt. Even as the disk evolves, the star continues its fierce transformation. Its color shifts as it transitions from cool, reddish-orange to the more stable, yellow-white glow of a main sequence star. Its spectrum changes as surface temperature rises. It emits more light as it contracts, gradually increasing in luminosity. The star's life is beginning in earnest. Its fusion furnace is stable. Its structure is defined. Its winds have calmed enough to allow planets to form in peaceful orbits. Its magnetic field, though still strong, is becoming more orderly. The chaotic infancy is ending. Maturity approaches. Soon the protoplanetary disk will thin into a faint halo. Planets will solidify into orbits. Asteroids will take shape from leftover debris. Comets will freeze into ancient reservoirs at the edge of the system. And the star, glowing steadily, will begin the long chapter of its life, billions of years of shining in quiet balance, a beacon in the galaxy. But before the system reaches this quiet order, the star must complete this stage of evolution. The energy, the winds, to the turbulence, all of it is shaping the architecture of the future. The young star is carving its identity into the cosmos. This is the adolescence of suns, a time of intense motion, rapid transformation, and fierce beauty. A time when a star learns to shine steadily. A time when worlds are scattered into motion around it. It is the cosmic equivalent of a heartbeat settling into rhythm after a long, breathless struggle. And soon, the system will be ready for the next chapter, the beginning of worlds. The system, well, the next 5-2. The young star's disk continues to change, not in sudden leaps, but in slow, graceful shifts that unfold over thousands of years. Each orbit of dust and gas carries the system closer to maturity. Each collision, each ripple, each spiral arm marks another step in the creation of a planetary system. The disk is no longer the chaotic, swirling mass it once was. It has become structured, layered, and dynamic, a vast, rotating workshop where gravity shapes raw materials into the building blocks of worlds. At this stage, the star's light has grown stronger. Its temperature has risen. Its once inflated outer layers are contracting. As they shrink, the star becomes more compact and more luminous, releasing energy more efficiently. This increased light warms the inner disk, driving chemical reactions that create complex organic molecules. These molecules cling to dust grains, forming icy mantles farther out and rocky composites closer in. The young star's ultraviolet radiation begins to evaporate, remaining gas in the disk's upper layers. This gas forms a thin, the glowing atmosphere that rises from the disk and gradually dissipates into space. What remains below becomes denser and more stable, a place where solid particles dominate. This transition marks the beginning of a crucial phase, the shift from a gas-rich disk to a dust-dominated one. And with this shift, the formation of planets accelerates. Protoplanets now sweep through the disk like sculptors. Their gravity pulls in dust, rock, and gas, shaping wide lanes of emptiness behind them. As they orbit, some collide with each other, merging into larger bodies. Others scatter into new orbits, creating chaos at the edges of stability. The star's gravity keeps everything bound, but within that binding, motion is relentless. A planetary system takes shape through conflict as much as through construction. The star's winds grow more influential as time passes. They reach farther into the disk, clearing away the remaining gas and pushing smaller particles toward the outer regions. These winds, though gentle compared to earlier stages, still carry enormous force. They sweep the inner disk clean, leaving behind only the larger bodies, rocks, protoplanets, and the seeds of future asteroids. Farther from the star, beyond the snowline, gas giants take shape. Their cores grow rapidly, feeding on icy material and dense clumps of frozen dust. Once they reach a critical size, they attract thick envelopes of hydrogen and helium. These giant planets become powerful architects of the young system. Their gravity stirs the outer disk, creating waves that travel inward and outward like ripples on a cosmic lake. Sometimes these giants migrate. They move inward or outward through the disk, pulled by gravitational interactions with the gas and dust around them. Their migration can disrupt smaller worlds, flinging them into new orbits or sending them crashing into the star. But it can also stabilize orbits, locking planets into harmonic dances that last for billions of years. The layout of a planetary system is rarely predetermined. It is sculpted by chance, by collisions, by timing, and by the subtle interplay of gravity. While planets take shape, the star undergoes its own transformation. Its magnetic fields, once wild and unpredictable, are settling. Flares become less violent. Sunspots grow smaller and less frequent. The star's rotation slows as its magnetic field channels angular momentum outward. What was once a rapidly spinning ball of plasma now turns more gracefully, its spin approaching the period it will maintain for the first third of its life. The star's internal structure continues to stabilize. Convection retreats from the core and settles into the outer layers. A radiative zone forms deep within, allowing energy to travel outward through radiation rather than turbulent motion. This transition reduces internal chaos, making the star more stable and less prone to dramatic outbursts. The light that escapes the star now has a more uniform quality, a sign of its growing maturity. As the disk thins, gaps become more defined. Some are carved by planets, some by pressure gradients, some by regions where dust has been swept away by winds or radiation. Each gap tells part of the story, a fossil record of the system's formation. The remaining dust glows softly in the star's light, scattering photons into space. From a distance, the disk appears as a thin, luminous ring around the star, like a halo shimmering in the dark. This glowing band is what future telescopes see when they search for young star systems across the galaxy. It is a signature of youth, a sign that planets may be forming or already formed. Over tens of millions of years, the disk becomes even thinner. The gas disperses almost entirely. Dust settles into stable orbits or falls into newly formed planets. The once massive disk dwindles to a faint belt of leftover debris, the beginning of an asteroid belt, a Kuiper belt, or something else entirely. Comets freeze into the cold outer regions, storing water and organic molecules that may someday visit the inner worlds. Meanwhile, the star enters the final stages of its adolescence. Its size has shrunk significantly from its early, inflated state. Its temperature has climbed to a stable, mature range. Its luminosity has reached the level it will maintain for the majority of its life. It has begun burning hydrogen in its core at a steady, predictable rate. It has truly become a main sequence star. This transition marks the end of the young star's chaotic beginnings. From now on, it will shine with quiet consistency. Its storms will still flare, but less violently. Its winds will blow, but more gently. Its light will warm the worlds around it, enabling atmospheres, climates, oceans, and possibly life. Yet, even in this calm maturity, traces of its youth remain. The scars of early collisions endure in the orbits of planets. The distribution of asteroids reflects ancient migrations. The chemical signatures in comets preserve the memory of the primordial disk. Everything that will ever happen in the planetary system, from the rise of life to the eventual death of worlds, is rooted in this early epoch. The star itself remembers in its rotation rate, its metallicity, its magnetic cycles. Stars carry the fingerprints of their birth long after their childhood ends. Now, with the disk fading and the star shining steadily, the system enters a new chapter. Planets cool and solidify. Atmospheres settle. Moons take shape. Rocky worlds develop crusts, mantles, and core structures. Gas giants stabilize their orbits, becoming the guardians of the outer system. Comets fall occasionally toward the star, delivering icy cargo to the inner planets. A solar system takes its final form not in a single moment, but across millions of years of refinement. And at its center, the once chaotic young star now glows with gentle, unwavering light, the heartbeat of a new cosmic family. The nebula that once sheltered the star gradually fades into empty space. The stars born alongside it drift apart, pulled by differential rotation of the galaxy. Some will remain nearby for millions of years. Others will wander to distant regions of the Milky Way. But all will share a silent bond, born in the same cradle, ignited by the same ancient laws, shaped by the same gravitational music. The young star, now fully matured, stands as a symbol of cosmic perseverance. It transformed from darkness to light, from chaos to balance, from collapse to ignition. And if planets orbit in the right places, and if conditions allow, life may take hold on one of those worlds, a new kind of ignition, and decision, quieter, but no less miraculous. This is the legacy of the young star. It is more than a burning sphere of plasma. It is a creator, a sculptor, a giver of warmth and possibility, a lighthouse in the cosmic dark. And now, as it enters the long calm of the main sequence, the system is ready for its next great epoch, the age of stable worlds. A newborn star is never just a point of light in the sky. It is a continuation, a new chapter in a story that began long before its ignition and will continue long after its light fades. Every star belongs to a lineage older than galaxies, older than the heavy elements that make planets, older even than the molecules that shape life. To understand the birth of a star is to understand the universe remembering itself, reorganizing its matter into new forms, and weaving new futures out of ancient threads. Now that the young star has entered the calm of the main sequence, it settles into its longest era. It will spend millions to billions of years burning hydrogen quietly, maintaining a balance so perfect that from the outside it seems effortless. But deep within, the star is a symphony of nuclear fire, a continuous churn of plasma, energy, and transformation. Hydrogen fuses into helium. Helium gathers slowly in the core. Photons bounce and scatter for millennia before breaking free from the star's surface and traveling across the galaxy. Each photon carries a whisper of the star's internal story, a fragment of its vast internal engine. This light is destiny. It warms planets, triggers chemical reactions, and sculpts atmospheres. It strikes dust grains between the stars, nudging them into new clouds. It illuminates nebulae, marking the regions where tomorrow's stars will form. And eventually, incredibly, this light may fall on eyes, living eyes, organic eyes on worlds that would not exist without stars. The young star, steady now, becomes a generator not only of energy but of possibility. Planets orbiting in the habitable zone may cool enough for oceans to form. Chemistry stirred by ultraviolet radiation may assemble into self-replicating molecules. Clouds may gather, rain may fall, continents may shift, atmospheres may thicken and thin. Across billions of years, life may rise, evolve, diversify, all under the steady gaze of the star at the system's center. But the story of the star is not limited to what happens around it. It is also part of a grander cosmic cycle. The star will one day die. Its death will scatter the elements it creates through nuclear fusion: carbon, oxygen, nitrogen, silicon, iron into space. These elements, forged in the star's later life stages, will drift into new nebulae. They will join hydrogen and helium, swirling into new clouds, new disks, new stars, new planets. Stars do not simply shine, they enrich. They seed the future. They prepare the universe for what comes next. Even now, in this moment, the star sets the stage for its future. Helium slowly accumulates in the core. The composition of the star gradually shifts. Thermodynamic changes unfold on timescales so vast they seem immortal from a human perspective. But nothing in the universe is truly still. Even stars evolve, inch by inch, across eons. The star's siblings, the cluster in which it was born, begin to drift apart. Galactic tidal forces stretch the cluster into threads. Nearby stars pull gently, slowly, over millennia. Some siblings will pass near each other again. Most will not. The cluster dissolves into the Milky Way, its children scattered across the spiral arms. Yet, in their spectral fingerprints, the specific ratios of elements forged in the same nebula, they will always carry a connection. Meanwhile, the star circles the center of the galaxy. It does not merely rotate, it orbits through a cosmic sea. The Milky Way's gravity pulls it in a grand loop that takes roughly 230 million years to complete. During that single orbit, civilizations may rise and fall, on any planet that forms around the star. Biological evolution may build forests, oceans, and mines. Ice ages may come and go. Entire species may bloom and vanish. And the star will simply continue, burning steadily, carrying its planetary companions through the galactic night. Along its orbit, the star passes through regions dense with stars and regions dark and sparse. It crosses spiral arms, where star formation is active, and drift through calm interarm regions, where molecular clouds are rare. Sometimes it may pass near a nebula, illuminating dusty tendrils with its light. Sometimes it may cross a spur of the galaxy, encountering rogue planets or ancient remnants of dead stars. Its gravitational wake leaves faint imprints in the interstellar medium, subtle ripples in the galaxy's fabric. But for most of its life, the star simply shines. It is an anchor of stability in a universe defined by motion. It is a point of order in a sea of entropy. It is the quiet heart of a growing family of worlds. Inside the star, fusion continues relentlessly. Hydrogen atoms slam together at unimaginable speeds, producing helium in a controlled chain reaction. Radiation pushes outward. Gravity pulls inward. The equilibrium holds. For billions of years, this balance will define the stars. Life, a perfect, delicate symmetry. Planets around the star move through their own cycles. Some worlds are battered by impacts. Some develop thick, swirling atmospheres. Some remain icy and distant. Some, if they lie in the habitable zone, may stabilize into mild climates where water can remain liquid. Volcanoes erupt. Rivers carve landscapes. Oceans rise and fall. Tectonic plates drift and collide. On at least one world, if conditions and chemistry align, life may spark. Perhaps in a shallow sea, perhaps in deep hydrothermal vents, perhaps in icy crusts warmed from below. Wherever it begins, life changes everything. It transforms atmospheres. It turns geology into biology. It introduces intention into matter. All of this unfolds under the watch of a star that was once nothing more than a whisper of gravity in a dark cloud. Eventually, after ages too vast for any single civilization to witness, the star will begin to change again. When its hydrogen supply in the core diminishes, the delicate balance shifts. Gravity gains the upper hand. The core contracts. Temperature rises. The outer layers of the star expand dramatically. It becomes a red giant massive, swollen, luminous in deep red light. Planets close to the star may be engulfed. Others may have their atmospheres stripped or altered. The inner system becomes a realm of fire. The star shines brighter than ever, but with a colder surface, its energy distributed across a larger area. In the core, helium begins to fuse into carbon and oxygen. These heavier elements accumulate, layer by layer, like the rings of a tree. But for a star the size of the Sun, fusion cannot proceed beyond carbon. The star lacks the mass needed to ignite the next stages. What happens next is both gentle and monumental. The star sheds its outer layers into space. These layers drift outward as a glowing bubble, a planetary nebula, named centuries ago by astronomers who thought they resembled distant planets. The nebula glows with vibrant colors: blues from oxygen, reds from nitrogen, greens from ionized gases. This glowing cloud expands for thousands of years, a final, beautiful blossom, marking the end of the star's active life. What remains at the center is a white dwarf, a stellar core, the size of Earth, but containing half or more of the star's original mass. It no longer fuses elements. It simply radiates its remaining heat into space, cooling slowly over trillions of years. Eventually, it will become a black dwarf, a cold, and quote, 8 chem, 8 quote, 8 quote, dark ember of what was once a sun. But the elements the star forged do not die with it. The carbon in its core, the oxygen in its shell, the nitrogen in its layers, these drift into space with the expanding nebula. Dust grains rich in metals, silicates, and water ice gather in swirling eddies. These materials seed the next generation of molecular clouds. From those clouds will come new stars, new planets, new possibilities. This is the cosmic cycle. Nothing ends. Everything transforms. Stars die so others may live. Nebulae collapse so suns may ignite. Dust becomes planets. Planets may become cradle worlds. Life may emerge. Think, dream all, because a star once burned hydrogen in its heart. The star that began in darkness, that rose into brilliance, that nurtured worlds, and perhaps life, now becomes part of the universe's raw material once more. Its existence was not a singular event. It was a link in a chain that stretches from the Big Bang to the farthest future. Every star tells this story. Every star continues it. Every star is a chapter in the universe's long memoir, written in hydrogen, shaped by gravity, and remembered in starlight. When the star's final breath becomes a planetary nebula, what seems like an ending is merely a scattering of ingredients. The elements released into space drift outward slowly, forming delicate filaments and expanding shells of gas. Over tens of thousands of years, these shells stretch into translucent shapes: ovals, rings, butterflies, spirals sculpted by magnetic fields, binary companions, or stellar winds. Their colors glow briefly in the cosmic night, a celebration of transformation before fading into the darkness. The nebula is a final whisper from a star that once burned fiercely at its heart. But though the nebula itself will disperse, its ingredients will not be lost. Carbon atoms, forged in the stars, late-stage burning, drift into the interstellar medium. Oxygen atoms join them, forming molecules of water in the cold regions of space. Iron, silicon, magnesium, difficult to forge elements created in older, more massive stars, are carried along as dust grains. These particles settle into molecular clouds, enriching the next generation of stellar nurseries. In this way, stars are the universe's alchemists. They take hydrogen, the simplest, earliest, the most abundant element, and through the long arc of their lives, transform it into the diverse ingredients needed for planets, oceans, atmospheres, and organisms. A newborn star may look pure and white, but it is built from dust that once belonged to countless ancestors. Every new star is a mosaic of old stars. Every nebula is a tapestry of ancient light, forgotten collisions, long-faded explosions, and cosmic inheritance. When gravity begins its work anew, pulling enriched gas together into dense, cold clouds, the cycle starts again. These clouds cool to just a few tens of degrees above absolute zero, cold enough for dust grains to cling together. Faint glimmers of infrared light reveal where collapse has begun. Protostars form. Accretion disks swirl. Jets burst from magnetic poles. And somewhere in that quiet, collapsing fog, a new star begins its slow path toward ignition. A new furnace is built. A new system takes shape. The universe repeats itself, not out of monotony, but out of an endless appetite for creation. But the story does not end even with the birth of new stars. The matter scattered by dead stars does more than simply join nebulae. It participates in an even richer evolution, the evolution of galaxies. Galaxies grow in complexity over billions of years as each generation of stars enriches the interstellar medium. In the early universe, stars were massive, bright, and short-lived, made almost entirely of hydrogen and helium. But as these first stars exploded as supernovae, they seeded space with heavier elements. New stars formed with more metals, giving rise to more complex chemistry. Planets became more diverse. Moons and rings and atmospheres formed with greater intricacy. Eventually, the conditions necessary for life emerged. Stars are not merely luminous objects. They are catalysts of complexity. They nudge the universe from simplicity toward richness, from emptiness toward structure, from chaos toward order. And they do so through cycles of birth and death, generation after generation. The star whose birth we followed through the quiet halls of a stellar nursery is now part of this vast story. Its light joins the wider glow of the galaxy. Its planets, if any formed in its disk, begin long, slow evolutions toward maturity. If life ever arises on one of those worlds, the star will be the constant presence in the sky, the giver of energy. Thank you, /Karn, buy one subscribe. The keeper of time, the guardian of seasons. Civilizations may arise. Gaze upward and wonder how such a brilliant sphere came to be. They may trace constellations, build observatories, and send probes into space. They may learn the physics of nuclear fusion, the behavior of gravity, the chemical signatures stored in starlight. And one day, they may recognize that their star, like all stars, was born in a nursery of hydrogen and dust. They may understand that everything they are their bodies, their oceans, their air, their memories was forged in the hearts of ancient stars, the calcium in their bones, the oxygen they breathe, the iron in their blood, the carbon woven into every piece of life. These elements were created in the last breaths of stars long gone. When those ancient stars died, they released their contents into space. From that enriched dust came new stars, new planets, new forms of life. The universe creates, recycles, reshapes, and renews itself continuously. Nothing is wasted. Nothing truly ends. Every death is a beginning. And so, the newborn star in our story carries within it the ashes of countless older suns, It is a continuation, not a departure. A chapter added to a cosmic book, whose pages stretch across time and space. For billions of years, it will shine. It will warm planets, melt ice, stir chemistry, and perhaps awaken biology. It will witness the rise and fall of geological ages. It will watch continents drift and oceans churn on any terrestrial worlds orbiting nearby. It will remain a constant presence in the sky, anchoring the rhythms of life. But eventually, the star will age. Its balance will falter. Its hydrogen supply will wane. It will swell into a red giant. It will cast off its outer layers. It will shrink into a white dwarf. And finally, over eons beyond imagination, it will cool and darken. Its light will fade. But its legacy will not. The atoms scattered by its gentle death will drift across the galaxy. Some will land softly in a newborn nebula. Some will be folded into the disk of a new star system. Some will help form the core of a planet. Some will dissolve into liquid oceans. Some may join the chemistry of life again. In this way, stars achieve a kind of immortality, not through eternal life, but through eternal influence. They live on in the matter they leave behind, in the worlds they help create, in the photons they cast into the dark, in the memories encoded in molecules. A star's birth is not just a moment of ignition. It is the opening of a path that will shape the universe for billions of years. A star's death is not a fading. It is a contribution, a gift, a preparation for the next cycle. The universe is full of these cycles, full of stars at every stage, newborns still wrapped in dusty cocoons, adolescents flickering in tea-towery storms, mature suns glowing quietly, giants swelling into red fire, white dwarfs cooling like cosmic embers. All coexist within the galaxy, like the varied ages of a vast stellar family. All play their role in the continuing story of creation. When we look up at the night sky, we see only a small fraction of this story. Each star we see is a survivor, one bright enough and close enough for its photons to reach us. But behind them lie trillions more. Stars hidden behind dust. Stars too far to glimpse. Stars not yet born. Stars long dead, but still whispering their presence through the dust that formed our world. The birth of a star, then, is not a simple event. It is an affirmation of the universe's nature, a living demonstration of cosmic patience, a reminder that great transformations come slowly, quietly, and with purpose. It is gravity's masterpiece, the result of billions of years of subtle, relentless pull. It is nuclear physics sculpting matter. It is chemistry waiting in the wings. It is the promise of worlds yet to form. And it is the promise of life. Because wherever stars gather, warmth follows. Where warmth flows, molecules move. Where molecules move, complexity grows. Where complexity grows, life becomes possible. The cycle of stars is the cycle of everything. The universe is not a static place. It is alive with motion, change, and renewal. Every atom in your body once sparkled in the heart of a star. Every breath you take contains molecules forged in ancient furnaces. Every memory you hold is shaped by the light of a star that warms your world. When a star is born, the universe expands, not in size, but in richness. When a star dies, the universe deepens in complexity. And between those two moments, ignition and fading, lies everything. A star is more than a point of light. It is the storyteller of the cosmos. Its birth is the opening line. Its life is the tale. Its death is the comma before the next chapter. And somewhere, in a distant nebula, another star is forming even now. Another core is collapsing. Another ignition waits. Another planetary system gathers dust and dreams. Another sun prepares to rise. The universe continues. The cycle goes on. And we made of stardust, bathed in starlight, always have been, always will be. As we reach the end of tonight's quiet cosmic journey, let your breath remain soft, steady, and unhurried. Somewhere in the distant dark, stars are still forming, slowly gathering light, quietly shaping themselves from clouds of dust, following the same patient rhythm that has guided the universe since its beginning. Feel the calm in knowing that creation itself unfolds in silence, that even the brightest suns are born from stillness, and that the cosmos grows not through rush, but through gentle, persistent transformation. Let that truth settle in you like starlight. Allow yourself to drift deeper into rest, just as nebulae drift into new worlds and new beginnings. Thank you for joining Science Sleep tonight. May the peaceful rhythm of the universe guide you into a night of calm, luminous dreams.